Alright, hey guys, what is going on? We are going to be talking about cost functions and backpropagation today within the topic of BioTech and its application in machine learning, or other way around, machine learning and its application of BioTech. And what we're doing here is we're sort of starting with the machine learning part. We're learning all the theoretical stuff, and then we're going to get into the other stuff that is biotech, and then we're going to start merging things together. We're going to do applications. I'm going to have my computer on the screen as well. We're going to go through these together. So let's go ahead and talk about cost functions today. So again, make sure to hit that like and subscribe button. You can go onto my Patreon page to support there, or you can become a member here on YouTube. And again, with just $10, you get access to all exclusive content, not just one particular playlist or anything like that. So let's go ahead and get started. So we had activation functions. There's also a function that we need to know called a cost function. This cost function is going to help us in understanding how we can update our weights as we continue with understanding our these neural networks. Okay, so let's just take an example here. So suppose we have these input layer nodes. These input layer nodes, since we're talking about biotech, we're going to make these input layer nodes be, one of them is going to be the size of the cell that we're looking at, and maybe some conformal microscopy image. Okay, we can take the age of the cell, maybe to document how long we've been incubating the cells or something like that, and then we can also take data directly from the microscope, right? So directly from the microscope is going to be, say, we can quantify the amount of yellow in the cell, or we can quantify the amount of blue in the cell. We can do that for different, however many nodes, however many colors we want to detect, okay? And we can also document maybe the shape of the cell. Maybe it's elongated, or it's a perfect sphere, or it's something like that, right? So this is going to be all the data that we put into our input layer. We then need to massage the data, put it into numbers, okay? That we'll talk about how that's done later. But then we then feed all this data into our hidden layer, okay? Now each hidden node is going to be like, well, okay, this guy here, for example, is taking in the size of the cell, the age of the cell, and the amount of blue in the cell, and it says, well, I think that all of these are indicators of the number of capsaces in our cell, for example. Or this guy, I don't even have connections to this guy. That was probably my mistake. If we take this guy here, this guy here is taking inputs from the age of the cell and the shape of the cell. And we think, okay, well, the age and the shape, that might be indicative of this being some NGF cell, right? So or not cell, right? These are a type of protein, NGF or NFG. But anyways, and then this guy here might be thinking, well, the amount of yellow in the cell and the size of the cell, that corresponds to the amount of connexins or something like that. And we could see, if we just look at this image, it looks like a lot of the yellow is on the edges of the cells here. Connexins tend to be on the edges of the cells. And so maybe that could this node could be looking for those features, okay? And so the output layer is going to be capsase, or the output layer is going to be, so all these hidden layers are going to feed into an output layer that's going to give it's going to give us some predictions. It's going to be like, well, okay, given all of this data, and I fed it into my nodes, and the nodes tell me, well, this neural network thinks that this person has Huntington's disease. That's what the output of this is going to be, Huntington's disease, okay? And then you say, okay, well, now here's where the idea of a cost function comes into play. The cost function is going to be like, well, this is what actually Huntington's disease looks like, right? So there's an actual number here that is correlated with someone who actually has Huntington's disease. We have all the data for this person that has this disease, and so we say this is that's what y is going to be. So y hat is our prediction. Y is going to be what the actual value is, we can compare the two, and that's a cost function. When we compare the two, so it's going to be the difference, half of the difference between the prediction and the actual value. All right. What ends up happening now is that we can then use this cost function to update our weights. All right, so let's take a look at what's going on here. So our cost function is going to be some number, right? So say the difference between these was 2, okay? 2 divided by 2 is 1, and so our cost function is 1, okay? And so this is going to mean, okay, so cost function, we get 1, with that number, we're going to go back now along these nodes, and we're going to update all these weights. It said the difference here was big enough for us to say, well, we need to go back, we need to update our neural network. Okay, it didn't do good enough. The cost function was too high, maybe. Okay, cost function was too high or too low. And so we need to go back, we need to take this number, whatever we get here, use that number to update our weights. Okay. All right. This process of updating our weights is called backpropagation. Okay, so, and this is an essential tool in getting better and more accurate neural networks. We can imagine doing this for multiple sets of data. So we have all this data, for example, and we say, okay, well, this data is going to be associated with some y hat value. This data is going to be associated with some y hat value. This one with some y hat value, and this one. We can pool all this together then. So there's a key thing here is that we don't have to pool all of them together, but suppose we do. We pool all of them together, we find their average or something like that. So we pool all of them together, and then we compare it to an actual value. Okay. This is going to be called batch gradient descent because we're doing this sort of in batches, okay, where we pool all this together compared to some actual data or to some actual value, and then get the cost function off of that, and then go back and update our weights from there. The goal here is to minimize the cost function again. The lower the cost function, the closer we are to the actual value, which means that the weights have all been adjusted to optimize for the prediction given the data. The value of y is a constant, and so our cost function is a function of y hat, right? This is just our actual value. This is what the actual data should look like. This thing is going to be the thing that fluctuates because this is the thing that we predict. So if we take the derivative of c, we can figure out if we need to increase or decrease the value of y hat. Right? So the variable, so c is a function of y hat, because this thing is the thing that's changing. So c is a function of y hat. So we could take the derivative we could take the derivative of c, derivative of with respect to y hat, like that. And when we do that, we get these slopes, right? So the derivative of c, the derivative of c, so c is our blue or black curve here, or blue curve, and that's c. The derivative is going to be tangent, right? So because based off of calculus, the derivative of some curve at any point is going to be the tangent line of the curve at that point. And we want to optimize this so that this derivative is 0, which is going to be down here. The flat line. We want to flatline this thing. All right. This is called batch gradient descent, where we want to minimize, or we want to get as close to the value of 0 as possible for the derivative of our cost function. All right, this is good. In this case, we found the global minimum for our cost function, right? So the idea here is that we found some global minimum, but we might have a cost function that looks like this, right? So where we have multiple minimums, right? We have a minimum right here, we have one right here, we have one right here, we have one right here. We even have maximums, right? We have maximums where the derivative is also 0. Right here. So we have many of them. So so the question becomes now, what we want to find this one. This is the absolute minimum. How do we do that? Well, Physically, this means that the sum of the total of our data did not suffice in finding the global minimum. Okay, so we need to do something called stochastic gradient descent to mitigate for this problem, to find the global minimum. And the idea here is that instead of doing batch gradient descent, right, instead of doing batch gradient descent, we're going to do them individually. So we start with data, get a y hat, get a cost function update just based off of this data, instead of pooling all this together. Okay, and we do the same thing: data, get a y hat, get a cost function update just based off of that one data. So we're actually doing this individually. For every experiment that we do, we are updating for after every experiment, as opposed to doing 10 experiments and then updating. Okay, you could think, well, this might take a long time to do, but it actually is not, right? The idea here is that this is actually not that difficult to do, because you're not pooling, right? When you pool the data, that takes time as well, and so there's not really a trade-off here, and so we get a more accurate neural network then out of this process. And this is because there's going to be more fluctuations as we see, more fluctuations which will enable us to traverse the cost function a little bit easier. So we do this, for example, we update we get a cost function, okay, and we're say get this value right here of our cost function. We do it again, say we get this value then, okay, for our cost function. We do it again, we get this value, okay. We do it again, eventually we will get to a lower value here in this process here. Again, it's called stochastic gradient descent. Okay. So now we have a workflow for constructing an artificial neural network. Randomly initialize the weights to small numbers close to 0. Input the first observation of your dataset into the input layer. Each feature is one input node. Okay, step 3 is going to be forward propagation from left to right. The neurons are going to be activated by the weights. The weights determine the degree to which each neuron is activated. And then step 4 is going to be compare predicted result to the actual result. That's going to be measured, and that's going to help us measure a generated error and a cost function. And then backpropagation. Using that generated error or cost function, we go from right to left. And this is the process of updating the weights. This is backpropagation. The learning rate decides how frequently we update the weights then. We're going to repeat, then you can repeat steps 1 to 5 and update weights after each observation. This is reinforcement learning or stochastic gradient. This is actually not, the wording here has to do with whether or not this is going to be stochastic gradient descent, but we can call this stochastic gradient descent for all intents and purposes right now. We can also call it reinforcement learning, or after a batch of observations, which is what we called batch learning. That was batch gradient descent. Okay. So, and then when the whole training set's passed through the artificial neural network, we're going to call that an epoch. Okay. So this is a rough set of rules that's going to get us started on making neural networks. What I want to do now is I want to sort of get a little bit more into the idea of the cost function, because this is just one cost function. There's many different types out there, and more generally, this thing can also be called the loss function. So a cost function, kind of synonymous with something called a loss function, but there's a key difference which we'll go into. Loss function in the next video. The cost function and the loss function, what they do is they just tell us what the difference is between our predicted data and our and the actual data. Okay. And so we have that, all right. So this is going to be part 1 of our agenda, to generalize this, understand a loss function. Okay. Part 2 is going to be, okay, we want to get into some BioTech stuff. How exactly are small molecules how exactly are small molecules and biologics predicted? All right. So this is the bio part, right? This is the bio part. We're not done talking about the tech part, but we have the bio part we need to talk about as well. Because again, this is a playlist on ML and its application in biotech specifically. Okay. And then from there, then we're gonna start going into examples. I'm gonna use Google Colab. Google Colab. We'll use a little bit of ChatGPT. We'll see how I do that. It's just to generate some data. So ChatGPT. And so, yeah, with that being said, we'll go ahead and stop there. Again, these ML videos are going to be a little bit shorter than the videos I do on physics and other stuff. So with that being said, I'll stop here. Make sure to hit that like and subscribe button, and I'll see you guys in the next video.